derivatives are basically slope, rise over run. But here's the catch. Now we're going to be talking about the slope of curves. And let's say I wanted to find the slope of a parabola. This is kind of an interesting thing to do because, it's curving, right? And for all of algebra, you talked about slope, like y equals mx plus b, and, slope was m, but like that's only for lines. How do you find the slope of a curve? Well, intuitively, you're already thinking about this in your day-to-day life, right? You already see hills. I mean, this is basically a hill, right?
Mhm.
And you talk about what is the slope of a hill, right? Like you talk about how steep a hill is. So, for example, if I asked you, how steep is the hill here? You would probably say it looks pretty steep. But if I asked you, hey, how steep is the hill here? You would say, I mean, less steep. And then what if I asked you, how steep is the hill here? You would say it's not steep at all. It's like flat. Like if we were using a number to describe how steep it is here, we would probably say 0, right? There is zero steepness, right? Does that make sense?
Yeah, it makes sense. We're just trying to find out during which point or which location on a hill how steep it is.
Yeah. Let's say the equation of this parabola is this. There is an equation for the slope, the derivative of this parabola. I'll just call it d, because why not? So there is a formula that will tell you the derivative, the slope at any spot on the parabola. And the formula is this. And you might be wondering, wait, how did you get that formula? Don't worry about it. I mean, you'll learn how to get that formula in a calculus class, but just don't worry about it for now. And actually, I'll write this using function notation. So let's say that this is like f of x, right? And this is like d of x. Okay, so I can plug in any point into my derivative function, and it will tell me the derivative at that point, the slope at that point. So for example, I could plug in 1. What if I plugged 1 into x? Well, I would get this, and I end up with 2. That right there is the slope. That is the derivative. So at x equals 1 on this graph, which is like, I don't know, like here or something, at x equals 1 on that graph, the slope right here is literally 2. The slope is 2 at this point. The formula just told me so, right? I could also plug in 2, and x equals 2 is more like over here. I feel like this my drawing is so crude that everything looks weird. Obviously, the gap here between 1 and 2 is way larger than the gap between 0 and 1. Pretend it's perfect. 2 is like going to be up here, all right? And I could try to plug 2 into the derivative formula. And if I do that, I get this. I'm literally replacing x with 2, right? And I end up with 0. So right here, the slope is 0 at this point. So that's how derivative functions work. Does that make sense?
Yes.
Cool. Um,
Derivatives are basically slopes at certain points on the parabola.
yeah, or it doesn't have to be a parabola. It could be anything.
Oh, okay.
We plug 2 into x. We plug 2 in to the derivative, and we got 0, if you remember. So right here, slope is 0. That's what we figured out when we did the math. And it kind of makes sense that the slope is 0, right? Because it's totally flat there at the top. Does that make
Yes.
sense? Yeah. So that's actually a really cool way to figure out hills and valleys. Maybe you talked about this kind of in your pre-calculus class, but there was like maximums and minimums, right?
Yeah.
And you can have like crazy graphs. What is an example of a crazy graph? I don't even know. Sometimes people are like what is the value here? What is the value of that valley? And in pre-calculus or in algebra, you had no way of knowing. But now in calculus, you can totally figure this stuff out, right? Because what you would do is you would find the derivative of this and then say, okay, I know that here the derivative has to be 0. Here the derivative has to be 0 because it's like flat there. So then you like set the derivative equal to 0, right? And solve for the points.
And this problem, the zeros at what appears to be 2, and here where it appears to be 2 3/4.
Oh, I kind of get what you're saying. If you find the derivative and it equals whatever, I mean, I won't do it. But then what you have to do, I guess I'll do it. It's like 5x to the 4 plus 12x squared plus 12x. Anyway, then you have to make d of x. You have to make that 0. So now you have to like solve for x here. I think what you were saying is you were saying the y values. The y here is 2. The y here is 2 3/4.
Yeah.
But when you're
Uh,
actually solving this equation, you're solving for x values. So you're not going to get
okay.
y values. You're going to get x values. So if you were solving this equation, you would factor out an x. Oh gosh. And then that means 0 equals x. Why does that pop up there? All right, bye pop up. And 0 equals this terrible equation that you probably can't even solve. But 0 equals x, that's one of the solutions, right? And then this one, you will not be expected to solve that, I'm pretty sure, because it does not have a rational solution, probably. See, Desmos actually tells me what the maximum is. And yes, it's some long decimal that they rounded. You're not, okay, you're not going to have to solve for x in a calculus class probably if you have some long polynomial where it's like x cubed or even bigger than that, right?